Welcome to Signal Science System subject classes. Now we are in the 6th chapter, that is discrete time Fourier transform. So in the chapter, this is the second video. Previously, we discussed about the derivation of the discrete time Fourier transform and its inverse Fourier transform. Here, again, I would like to write this discrete time Fourier transform formula. See, this is x of n. So x of n. So x of n, it is a aperiodic discrete time signal. This is discrete. So discrete time signal. And so it's a discrete time Fourier transform. It is denoted by the x of square bracket e power j into omega. That equal to. So in continuous time, we have taken the Fourier transform that is called x of j omega. But in case of the discrete time Fourier transform, we are taking e power j omega. Why we are taking like this comparing to the continuous time? We will clearly discuss in the Laplace transform and Z transform. So discrete time Fourier transform, this is a discrete time Fourier transform that equal to, so sigma x of n, so x of n from minus infinite to the plus infinite into e power minus j omega into n. So this is a discrete time Fourier transform formula, and inverse Fourier transform that equal to x of n. So x of n that equal to 1 by 2 pi. So this x of e power j omega is a continuous. Then we should take integration instead of the sigma. So this x of e power j omega is a periodic, even though x of n is aperiodic, but x of e power j omega is a periodic. That you should remember. It's a very, very fundamental concept. The periodicity equal to also 2 pi. So x of e power j omega into e power minus j omega n into with respect to d omega. So these are the discrete time Fourier transform pairs. So in general, you can write x of n, its Fourier transform. So that equal to x of e power j omega. So this is discrete time Fourier transform. So this is the two equations. Already these are discussed in the previous classes. Now I'm taking one example. For that example, we have to do the discrete time Fourier transform. So that is problem. The problem. So the problem is one aperiodic signal that equal to x of n that equal to a to the power of n into e of n. So this is the upgrade signal. You know very well this a to the power of n. So this mod is very important in the condition. Otherwise, we can't do that. So for this case, what is the discrete time Fourier transform? Discrete time Fourier transform of x of n is. So this is a problem. So we have the formula, that is for the discrete time formula, that's x of e power j omega equal to sigma n from the minus infinite to plus infinite x of n into e power minus j omega into n. So these are the discrete time Fourier transform. So the given x of n equal to a to the power of n into u of n. This a power n is multiplied by the unit step. It means that it is having the magnitude for the positive values of the n. So it is having the value from the n 0 to infinity. So minus infinity to 0, there is no signal. So for while writing the limits here, for example, so sigma from the n from the 0 to infinite, the x of n is nothing but a to the power of n. Here I am writing, so x of n that equal to a to the power of n for n greater than or equal to 0, 0, n less than 0. That is the case. That's why a to the power of n is multiplied by u of n. Why? Because u of n, you know that it is having the magnitude for the positive values from the 0 to infinity. So then you here no need to write the u of n. You should remember. So then e power next term is e power minus j omega into n. So both are having power equal to n. E power n, e power minus j omega whole to the power of n. Yes. So in that way, n 0 to infinite, so a into e power minus j omega to the power of n. So one GP, you know, GP, for example, in GP, r to the power of 0 plus r to the power of 1 plus r to the power of 2 plus dash 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 r to the power of r to the power of n, r to the power of n. The sum of the terms equal to the sum of the terms r to the power of something n, that is a variable. You can write capital N. So up to n, capital N. So that equal to the sum equal to 1 minus r to the power of n plus 1. So number of terms by 1 minus r. The condition r must be sorry, not for that. Okay, for n, if n leads to infinite, so this formula, so n 0 to infinite, so r to the power of n that equal to 1 by 1 minus r. The condition here, the condition is the r must be less than 1 only. For that only. So this is here also same. See, the second upper limit goes to the infinite. So this is r. Then already we know that this is mod a. It's a mod of a less than 1. So the mod of a less than 1, this mod goes to 1. So this is automatically it is less than 1. Why? Because here we have taken mod of a less than 1. For that condition, directly here I'm writing that x of e power j omega that equal to 1 by 1 minus that r value equal to a into e power minus j omega. So this is the case. So you should remember in discrete time, in whether it is in the discrete time Fourier series or Fourier transform, we are always using this GP. So this is geometric progression, GP. So these are the GP terms. Next problem. One discrete time signal, that is so x of n, it is having magnitude 1 for the mod n less than n1. Otherwise 0. Mod n greater than n1. So this is aperiodic. So for this case, discrete time Fourier transform of x of n is already in periodic. So this is a period signal. We know that this is a periodic. So with help of the Fourier transform equation, then we can easily find it. Here I don't want to solve that one. Already have done in the discrete time Fourier series. So here simply you know that in derivation that x of e power j omega is taken as ak into capital N and omega that equal to k into omega naught. The relation between the discrete time Fourier transform and discrete time Fourier series. So for the discrete time Fourier series, see in discrete time Fourier series, x of n, this is the periodic signal, that is 1 for the mod n less than n1 and n1 to the mod n to the half of the time period, n is the time period that equal to 0. So it is defined for only one time period. So it is repeating for every time period. So for this case, the discrete time Fourier series, already we have done this one. So here I'm directly writing that the Fourier series coefficient AK, so AK equal to sine of k omega naught n1 plus 1 by 2 by n into sine of omega naught k omega naught by 2. So this is the case. So this is the Fourier series coefficient. So we know that AK into n, that is nothing but Fourier transform, discrete time Fourier series. So x of, so directly based on the discrete time Fourier series, here I am writing e power j omega, so that equal to sine of omega. Otherwise, right, actually ak into n, this is right, like x of e power j k into omega naught, so that equal to ak into n, so that equal to sine of k omega naught into n1 plus 1 by 2. Already we sent n to the left side, then there is no n, then there is only sine function that equal to sine k omega naught by 2. Then, so the x of e power j omega, so that equal to sine omega sine omega n1 plus 1 by 2. So sine omega by 2. So I'll show you in discrete time Fourier series. The question is, see, this is a question. So x of n equal to 1, so this is a periodic signal. So in substitution, then after simplifying, so same procedure, there is no difference here. We'll get in final step, ak equal sine k omega naught into n1 plus 1 by 2 by n into capital N into sine k omega naught by 2. So this is a Fourier series coefficient. So similarly, so I don't want to prove again. So with the help of the Fourier series coefficient formula, simply we know that. So it is also useful how to remember the same for periodic for Fourier series and Fourier transform. So simply just ak into capital N is nothing but Fourier series coefficient, Fourier series transform, and k omega naught must be replaced by the omega. That is the case. So these are the examples. Next class, we will discuss properties of the discrete time Fourier transform. Thank you.